to work on example 2. We just review how the notation, different notations for second derivatives, such as that one. It doesn't mean d squared, it just means the second derivative of position, which is function f. It could also be function s, so if that's the case, acceleration will be the second derivative of position. So let's answer example 2, and we do have, and I'm going to show you some animation so that the question makes more sense. Suppose the position in feet of an object moving horizontally at time t in seconds is, and we have the equation for it here. So s for position, that's the output, and then t for time. And that equation is true for t from 0 to 5. And we're talking about seconds here, not hours, seconds. So assume the positive values of s correspond to positions to the right side of s equals 0. So if we have positive, it's on the right side. If we have negative, it's on the left side. Okay, so graph the velocity function on the interval, blah, 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 blah. So are they giving us the equation for velocity? Where are they giving us?
The equation for position.
Okay, but you guys can find velocity pretty easily, right? Because you know it's the derivative of position. So that is 2t. Well, what is the derivative of, oh yes, minus 5. Sorry.
Oh, okay. Oh.
Yeah. So that would be velocity, and that's it.
Oh. So does this apply in physics too? Like,
yes.
Like for reals?
Yes, it's the same thing. Yes, I promise. Okay, so now graph the velocity function on the interval and determine when the object is stationary, moving to the left and moving to the right. So let's see. The object. Take it down. I was playing with this earlier. Okay, so the 0 here, let me make sure I'm in the right problem. Is this the right problem? Yes. So this is how the position, if you were to graph it, that is how it will look. Okay? All right, I'm going to play it again, but I want you to notice something. Just like before, when Maxwell told me it's going back to the station, right? And it went back to the x-axis, so the position was 0. That's the same thing that is happening here, right? So it's going back to position. This is s, this is the position, so the position is 0. So if the position, I have to reset it, right? So if the position, remember what they say, if the position is positive, then the point is moving to the right side. But do you guys see the position being positive at all?
No.
It's always negative, correct? So that's why the object is just moving to the left. Okay, so I'm going to play it again. So it moves to the left. That's the furthest it gets, to -6, and then it starts moving back to the right, and it goes back to the origin, where it came from. Okay, so now let's see at what times it will be stationary, all right? And so if we look at this graph here, I hope I'm going to play this one. So, to be stationary, if that is not moving, right? This is there. So if it's just there, what number will the velocity equal to? 0. So you already know if this is the position, the one that looks like a parabola, the one in red is the derivative, which is the velocity. Okay? And you can see very clearly that right here, it's where the velocity is 0. And you could also see that because here the slope is 0. It's a turning point, in fact. So let me play it for you. Is all this physics making sense? With the animations? Okay. So let's see. So it goes to the left. And then it stops right there. You guys see that? For like a tiny bit, like a little longer than the others. And then it goes back. So go ahead and answer that question. It's stationary right at, what was it, 2.5? Okay. Now, how we would find that algebraically was very simple. We will say, we take the derivative Okay, so on your slides, I actually copied the answers from the textbook because I wanted to focus more on the showing you the animations. So you can see right there. And so if we take the derivative and we equal it to 0, this one, the velocity equals 2t minus 5. If we equal the velocity to 0, then we're going to solve for t, and we will get 5 is equal to 2t. So t is equal to 5 over 2. So it's either 5/2 or 2.5 seconds, which is right here, 2.5. And that precise time, the velocity was 0. Okay, what is the next question?
Describe the motion of the object.
Okay. And is that B or?
That is C.
That is C. Okay.
Did we skip B? Did we skip?
It feels like it. Hi, Ms. Orchard. Hello. Okay, so we did skip a little bit of, actually the whole thing of B. So we did not finish answering here, but the equation was on the other slide. So here at t equals 2.5 or 5/2 seconds, that's where the velocity is equal to 0. So now graph the acceleration function on the interval. And now pretend that you have not seen the graphs. And if you know that the position is a quadratic, right? And then you know the velocity is a linear. So now you know the acceleration is going to be constant. Very good. And that is because the velocity has the same slope all across. The velocity didn't really change. And so the slope here, I mean, you could pick 2 points and calculate it, or you could look at the equation and see it is 2, right? And so the acceleration is here all the way. It didn't change at all. And that's just because the velocity remained constant. Okay? And so with the units of acceleration, we do have to be careful though. And remember how we had like that dt squared? And I told you it was going to be like time divided by time again. So right there, that's why acceleration, the units are distance over time squared. Because you do that double division by time. That make sense? Cool. All right. So that was part B, correct? What was the acceleration? And right here again, acceleration is the first derivative of velocity, and it's also the second derivative of position. Okay, now part C. Let's read the question. Can someone read it, please?
Describe the motion of the graph.
Of the object, I'm sorry.
The graph doesn't move.
Okay. So let's see. Look at the position. Was the position ever negative? I mean, ever positive?
No.
No, right? The position was negative the whole time. But when was it the most negative?
When it negative 2.5.
It was -6, right? At right here, 2.5 seconds. So then, what are we even talking about? A particle? An object, right? Because I lose track if it's a car, an object, a particle, you know. I know what they're doing, I just don't know what they are. Okay, so the object, at initial position, right, it was at 0. But then it started moving in the negative direction. And remember, it was established at the beginning of the problem that the negative direction was going to be to the left of its original position. And then what was happening to the, why does it say with decreasing speed? Oh, yes, it does. How do you guys, how would you connect that with the graph? That the speed is decreasing.
If you look at the velocity graph, the magnitude of the speed, the magnitude of velocity decreases up until 2.5. So you could see, did I say that all right?
Yeah.
Yeah, okay, so the magnitude of the velocity decreases, so you can say that the speed is decreasing for the first 2.5 seconds. Do you see the velocity? Yes, no? Maybe so?
To the, hold on, I'm trying to, increasing speed, okay, so we know it's moving to the negative direction to the left, right? With decreasing speed. I don't know, I'm not very convinced.
Well, yeah, as you approach 2.5, the magnitude of the velocity just keeps getting smaller. So like, the more left you go,
This one?
yeah.
Yeah.
The more left you go, the bigger the negative number is. So it'll be like -5 meters per second, and the closer you get to 2.5, it'll be almost 0 meters per second.
0 meters per second. Oh, and then it goes, and then it's positive.
It gets bigger again.
Okay. So right here, it is decreasing because the derivative is negative.
Because the derivative is approaching 0.
Yeah.
So it's technically becoming positive, but we're looking at like the magnitude. So if we look at the magnitude, it's like 6, 5, 4, 3.
Yeah, since speed is the absolute value of velocity, it is decreasing, even though the velocity.
The velocity itself is increasing.
But the magnitude is.
Oh, okay. So it's speed. Not velocity. Okay. Alright. What was the question again?
Describe the motion.
Okay. So now that I know it's speed, so from there to there, the speed comes to rest momentarily. So this was at that 2.5, right? The one that we said it was gonna change. And then the object moves in the positive direction to the right with increasing speed, reaching its initial position. Okay. So remember how we first started saying that if the position was negative, it was moving to the left, correct? So it was moving further and further and further to the left, and then it started, even though it's still below the x-axis, here it's moving to the right, just because it's going up again. Okay? Alvin, don't be distracting my student. I know you wish you were in this class now. And then, so we have during this time interval, the acceleration is constant. How do we know this if acceleration is constant? Yeah, it's the horizontal line, right there. You also know that the second derivative of a function of second degree is going to be a constant, right? Okay. Now, describing your own words, the velocity of an object that has a positive constant acceleration Could an object have a positive acceleration and a decreasing speed? Yes, some. What? It's time already? What?
Or are they getting down? I was like,
Why? That was so quick.
I
Okay.
love free fall. This is the fastest class ever.
I know.
Like,
Okay, so we'll just continue on Wednesday and then
That was so fast.
Since I did it,
yeah.
But